Hello everyone, this is Ashwini, Assistant Professor from EC Department of SA Engineering College. So today I am here to give some introduction about the GATE lecture series on section number 2, Network Signals and System. So here comes our institute vision and mission, followed by our department vision and mission. And when we talk about network theorem, apart from the normal method like Kirchhoff's voltage law and Ohm's law, there are still many network theorems available which can be useful for solving any complex theorem. So in my earlier video regarding this GATE lecture series, I completed discussing about superposition theorem, and today we are about to learn the next theorem, namely Thevenin's theorem and Norton's theorem, and problems associated with both the cases. So coming to Thevenin's theorem, and the definition goes like this. Thevenin's theorem states that it is possible to simplify any linear circuit irrespective of how complex it is to an equivalent circuit with a single voltage source and a series resistance. So as I said already, apart from Ohm's law and Kirchhoff's law like voltage law and current law, there are many theorems available which also gives a different perspective of analyzing any complex circuit on its own way. Now here, as you can see, as per the definition of Thevenin's theorem, any linear network, any complex linear network can be possible to simplify just by a single voltage source, as you can see here, Vs, and a single resistor Rs. So on the other side, as you can see, any linear network containing several EMF and resistance is possible to be converted into a circuit with single voltage source Vs and resistance Rs. So this is the ultimate aim of a Thevenin's theorem. Any complex circuit can be converted into a simplified circuit with voltage Vs and resistor Rs. So as you can see, a Thevenin's equivalent circuit is shown in the image. Here we can see that multiple resistive circuit. So here you can see multiple resistance, right? So a collection of resistors are now being replaced by a equivalent resistance Rs, and multiple EMF are replaced by Vs. So this is how the definition of Thevenin's theorem go. And as we proceed to solve any complex problem, there are certain steps to be followed. As you can see here, there are some steps that are very crucial for solving Thevenin's equivalent resistance, voltage, and drawing the Thevenin's equivalent circuit. So initially, where you have to remove the load resistor RL. So in any circuit, the load resistor will be given. So it is R work to find out what is this load resistor. So upon finding the load resistor, keep removing the load resistor or any component which is connected across the terminal where it is required to find the Thevenin's equivalent circuit. Coming to the second step, we have to determine the Thevenin's equivalent resistance value. So as we saw in the previous slide, a network with many resistance value are now being replaced by a single resistor. So we need to find out an equivalent resistance value, RTH. The procedure for finding RTH is we have to kill all the sources, killing the sources. So here killing means voltage sources should be short circuited and current sources should be open circuited. So this is how we can make the effect of voltage and current to zero in order to find the value of RTH. Now coming to the third step, you have to determine VTH. So here this VTH we will call as Thevenin's voltage or open circuited voltage. So this Thevenin's voltage or open circuited voltage is obtained by calculating the voltage between the open terminals A and B by usual circuit analysis method. So here to find this VTH, we can use any methodology for finding the value of the Thevenin's voltage. Now, as we proceed further, here are some applications of Thevenin's theorem. So, Thevenin's theorem is used in the analysis of power system, and it is used in source modeling and resistance measurement using the Wheatstone bridge. And though there are applications and this is a useful method for solving any complex circuit, still there exists some limitation. The first limitation of Thevenin's theorem is it is used only in the analysis of linear circuit, and followed by the power dissipation of the Thevenin's equivalent is not identical to the power dissipation of the real system. So taking into account all these things, we will try to solve some problems using this Thevenin's steps. So the first question goes like this: find VTH, RTH and the load current IL flowing through and load voltage across the load resistor in the circuit using Thevenin's theorem. So the requirements are, you need to find out what is VTH, Thevenin's voltage, RTH, Thevenin's resistance or the equivalent resistance, and load current IL, right? So just upon looking at the circuit, one can easily find out where the load resistor is actually located. So it is exactly the place over here, the load resistor RL, that is 5 kilo ohm, is situated, right? So I think you can understand the load resistor is situated or it is located across the terminal A and B bearing a value of 5 kilo ohm. So it has been asked to calculate what is the current flowing through the 5 kilo ohm. So as per the steps of Thevenin's theorem, first step, you have to remove the load resistor. So one can easily find out the load resistor is RL 5 kilo ohm. So kindly remove that 5 kilo ohm from the circuit. This is being the step number 1. Coming to step number 2, after removing the load resistance, this particular region becomes open circuited, because once you remove a component or a branch, right, this place becomes open circuited. Now this is the place where we are supposed to find out VTH or open circuited voltage. So I have to find out this open circuited voltage across this place after removing my RL, right? Now after removing RL, I have to calculate Thevenin's voltage by determining the current that flows through the 12 kilo ohm and 4 kilo ohm resistor. So one must understand, once this 5 kilo ohm resistor is removed, this becomes open circuited, but still I want to find out what is the value of voltage flowing across this region, right? So since this is not possible because of open circuiting, I am actually in search of a parallel branch where the same voltage can exist. We all know very well, in parallel circuit, voltages are same, right? So instead of finding the voltage across AB terminal, it is equivalent to finding the voltage across this 4 kilo ohm as they are parallel to each other. So now we are making use of this 4 kilo ohm to find out what is the voltage appearing across it, right? Now I know what is source EMF, I know what is the resistor, right? And since this 8 kilo ohm is connected to the open circuited region, the effect of this 8 kilo ohm becomes 0. So after removing this 5 kilo ohm, this place becomes open circuited. So this 8 kilo ohm, the effect of this 8 kilo ohm is negligible. So we can easily remove, we cannot take into account the effect of 8 kilo ohm. So our circuit is only restricted to this 48 volt, 12K and 4K. So this becomes a simple circuit, a loop, right? Actually a loop is formed with voltage and resistor. So it is by Ohm's law, is can easily calculate what is the current I. So current I is equal to, as you can see here, current I is equal to V by R, that is 48 volt divided by 12 and 4, since they are in a loop, right? They are connected seriously. So you can add this 12 and 4 together. So 12 plus 4 is 16. 48 divided by 16 is going to be 3 milliamps. So the amount of current flowing inside this loop is only 3 milliamps. So once I am able to find out what is the current flowing through this 4K, I am able to find out the voltage. So again, by Ohm's law, we can calculate V is equal to I into R, right? So you can see here very clearly, as there is no current flowing through the 8K resistor, there is no voltage drop across it. So that is the reason we have not taken into account the 8K. We are very much confined only with that 12 kilo ohm and 4 kilo ohm. And here 12 volt will appear across the AB terminals, hence the Thevenin's voltage or the open circuited voltage for this circuit is 12 volt. So after finding VTH, we need to find out step number 4, that is finding the Thevenin's equivalent resistance, RTH. So to find RTH, what is the procedure? The procedure is you have to kill the energy sources. So the energy source as you can see, it is a voltage source. So how can I kill the energy source? So killing is something making its effect equal to 0. So to kill this energy source, I have to make this voltage source short circuit. So this is what being made here. So this voltage source is removed and that region is short circuited, so that the value of that 48 volt is becoming 0, right? So this is our understanding. Now with this current setup, we have to find out what is the RTH, that is equivalent resistance. So one can easily understand, since this region is short circuited and two resistors are connected, right? So I can say this 12 and 4 are parallel to each other because of this short circuit. After removing 48 voltage, the region is getting short circuited, and because of this short circuit condition, this 12K and 4K are said to be parallel to each other. So here as you can see, 12 and 4 are parallel, 4K, 12K are parallel. I think you can understand clearly. 4 and 12 are parallel, and this combination after simplification or after reduction, it will be in series with 8K. So to show you very clearly, right. So this is how, like, short circuited, I have this and this and this. Right. So this particular region is short circuited and I have 4K, sorry, this is 12K, 12K, this is 4K, and here I have 8K. Right. So we are about to find out what is RTH. So since this region is short circuited and here there is a presence of node, right? So we can easily determine 12K parallel with 4K. So what is the net result of parallel? 12K into 4, this is equal to 12K into 4K divided by 12K plus 4K. So this we know very well, how to solve resistors in series and parallel, right? So this result, so how can I modify this diagram? So this is equal to a single resistor, right? I am going to replace this as 12 parallel with 4 and 8. Now one can easily determine these are connected in series, so the net RTH is supposed to be 12 parallel with 4 plus 8, because there is no more short circuit or any node present after reduction. So this is what we are trying to show here. So I think one easily can understand. So because of short circuit, these two are said to be parallel, and this reduction, the result after reduction, will be in series with 8. So you can get the total Thevenin's equivalent resistance as 8K plus 3K. That is, this 8K is this value and this 3K is the result of 4K parallel with 12K. So totally now the value of RTH is equal to 11 kilo ohms. So this is going to be our step number 5. So as you can see, initially we started calculating VTH, then we proceed to find out what is RTH. Next comes our Thevenin's equivalent circuit. So to draw a Thevenin's equivalent circuit, initially when you saw slide number 1, definition for Thevenin's equivalent circuit, you might remember any linear circuit can be drawn, right, can be simplified as a circuit with single voltage source and RTH, that is multiple resistance, are reduced to a single resistance value, where we will call this as RTH. Right? So I am here to just give you how to draw the Thevenin's equivalent circuit. So any complex circuit can be redrawn as Thevenin's equivalent circuit by simply having VTH in series with RTH followed by the load resistance RL. So VTH we calculated as 12 volt RTH is nothing but 11 kilo ohm, and RL initially the resistor which we removed, right? So that can be included here. So this is called as Thevenin's equivalent circuit. Now it is also possible to find out what is the load current flowing through this RL. So the formula goes like this: IL is equal to VTH divided by RTH plus RL. So as per the requirement, we completed finding VTH. Next is our RTH, and with the help of VTH and RTH, one can easily predict what is the load current IL. Right. So as I said, load current IL. Just now I gave you example how to calculate load current IL. So it is VTH divided by RTH plus RL. So what is RTH? 11K. What is RL? This is the resistor initially we removed, right, in order to calculate our open circuit voltage, that is VTH. So kindly include that. So you will get what is IL, and the load voltage. Yes, obviously because of Ohm's law, if any two parameters are known, right, out of three, that is V, I and R, we can find out the other one. So since I know what is IL and I know RL, I am able to find out what is the voltage, that is load voltage. So VL is equal to IL, just now we completed, at as 0.75 milliamps multiplied with RL, which is nothing but 5 kilo ohm. So the load voltage is said to be 3.75. So now one can easily understand how to apply Thevenin's theorem step by step in order to find out the various parameters, that is voltage and current. So next, coming to Norton's theorem. So the statement goes like this: any linear two-terminal circuit can be replaced by an equivalent circuit consisting of a current source IN in parallel with a resistor Rn. So this is the Norton's circuit, right? Condition to draw a Norton's equivalent circuit. So we need a current source IN in parallel with a resistor Rn, where this IN is called as the short circuit current. Very important. So you must have a clear understanding between what is Thevenin's theorem, steps in Thevenin's theorem, and the parameters that we use in Thevenin's theorem against the parameters that what we will use in Norton's theorem. So in Thevenin's theorem, it is VTH. Initially we will calculate VTH, and here the procedure starts by finding what is called as IN, that is short circuit current or Norton's current, followed by Rn. Rn is your Norton's resistance value. Norton's resistance value and Thevenin's resistance RTH both are same. Right? So as you can see, IN is the short circuit current through the terminal, and Rn is the input or equivalent resistance at the terminal when the independent source. Right? So as you can see here, any linear two-terminal network, originally it will be like this. So upon applying this Norton's theorem, right, you can convert this circuit like this. So the requirement is you have to convert this into this by having a current source in parallel with your Rn resistance, that is Norton's equivalent resistance. The same thing when it goes to Thevenin's circuit, Thevenin's equivalent circuit, you have to replace this current source by an voltage source, and this parallel resistor should be a series resistor, because we know very well always your voltage source should have a resistor connected in parallel, that is the internal resistance connected in series, whereas for a parallel circuit a current source should have always have its internal resistance connected in parallel, right? So these are the mandatory things to be followed. Now what is the reason we go for Norton's theorem? So it simplifies the network in terms of current instead of voltage. So if our concentration is more towards finding out the current contribution instead of voltage, then we can prefer Norton's theorem, and it reduces a network to a simple parallel circuit with a current source and a resistor, right? So this is what our understanding. Any circuit can be converted into a simple parallel circuit with a current source followed by a resistance value. And this is the close relationship between Norton's theorem and Thevenin's theorem. So any linear two-terminal circuit can be converted into a Thevenin's equivalent circuit with VTH and RTH in series. Coming to Norton's, right? The same two-terminal network using Norton's, this is the equivalent circuit. So what difference you can observe? So closely find VTH, voltage source is replaced by current source, and the resistor RTH, which is initially series for Thevenin, will be now called as RN, and it should be placed parallel. Okay, so this is how. Now why this has been shown here is, you have to understand, even one can derive the parameters for Norton's theorem directly from Thevenin. So once you know what is the Thevenin equivalent values, VTH, RTH, it is possible to find out IN and RN also. And similarly, from Norton, one can easily find out the parameters related to the Thevenin. So that is the reason here we are trying to find out what is the close relationship between Norton. They are already having a very close relationship, so that one can be found out from the other. And here are some of the steps to determine the Norton's equivalent resistance Rn. So calculate Rn in the same way as RTH. There is no much difference. This is the same procedure whatever we have adopted in finding Thevenin's equivalent resistance RTH. The same has to be followed here also. And the techniques whatever we can use for reducing the series parallel combination, you can go for source transformation, that is Thevenin and Norton resistance are equal, right? So you can go for source transformation, and to find out the Norton current, we can determine the short circuit current flowing from terminal A to B. So this point has to be noted very clearly. Right, so for Norton's equivalent circuit, the very first step is, upon finding the load resistance, the load resistor has to be removed, and that particular place or branch has to be short circuited. Right, whereas in Thevenin's, we will remove the load resistor and we will make the place open circuited, and we will try to calculate voltage across this open circuited condition. Now coming to Norton's theorem, identifying the load resistor, removing it, and after removing, the branch has to be short circuited, and in that short circuited branch we are about to find out the current, and that's it why it's called as short circuited current. Right, so this step is very important. So this short circuited current, we will name it as Norton's current. So IN or ISC, both are same. And here comes some of the limitations of Norton's theorem. It cannot be applied if there is a magnetic coupling in load and circuit elements. If the load is in series or in parallel combination with dependent sources, then Norton's theorem cannot be applied. And some of the applications of Norton's theorem, it is applicable in replacement of a large part of the network to a simple circuit. So actually Norton's circuit theorem is very much helpful for reducing the complexity of the circuit. Coming to the second application, it is used in the simplification of network in terms of current instead of voltage. So we will give more preference to current rather than on voltages. And the third application, it also helps to accomplish a maximum transfer of power. So maximum power transfer could also be accomplished with the help of Norton's theorem. And here are some sample solved problems, that too in the form of MCQs. So as you can see, the first question, the Norton's, find the Norton's equivalent current between the load terminal AB. So what will be the Norton's equivalent current between the load terminal AB, right? So there are 4 options given, and the reason why the option number 2 has been selected is, see, the given circuit, right, we need to find out the Norton's equivalent current between the load terminal AB. So the load terminal is A and B. So what is step number 1 of Norton's theorem? After identifying the load resistor, remove it and short circuit it, right? So this will be the equivalent. So upon identifying the load terminal, I have to short circuit, right? So this particular curve, right, this is actually a line, short circuit line. Instead of drawing it straightly, I have just make it like a bend. So this is the short circuited region, and we are about to find out the short circuited current IN across here, right? So now how to find this? So I have a 10 ohm, right? 10 amps current. So we have a 10 amps current here, 2 5 ohm resistor followed by a 15 ohm, right? So 2 5 ohm resistor and followed by a 15 ohm resistor, and here we also have short circuit. 5 ohm, 5 ohm, 15 ohm and short circuit. Now how to find out which short circuit current, that is current flowing through this region? See, to solve this circuit we can understand any parallel branch, that is any branch which is parallel to the short circuited region, right? The effect of this resistor will be equal to 0. So whenever a resistor is in parallel with a short circuited region or a branch, its effect is negligible and its value is said to be 0, right? Now don't take into account what is the value of 15. Now our reduced circuit is only 10 amps and 2 5 ohm resistor. 10 amps and 2 5 ohm resistor. Now with this reduced circuit, one must be able to understand or find out what is the current. So for which we are going to make use of current division rule, because the input is also a current value and the expected output is also a current value. So by current division formula, the short circuited current ISC is equal to the current, incoming current, right, into what is the parallel branch of this short circuited region. So actually this is the 15 ohm which we are actually eliminating. So opposite of this short circuited region is 5, right? So just opposite of this short circuited region is 5 divided by sum of parallel resistor. So neglecting this 15, still we are left out with 2 resistors, 5 and 5. So sum of parallel resistors. So here comes 50 divided by 10. So my answer is 5 amps. Right? So this is the understanding. So that is the reason option number 2 has been chosen. Right? So here this is what I am trying to explain. One more. So what is the Norton current at terminals A and B in the given circuit? Norton's current at the terminals A and B. Right? So A and B is your load right now. And step number 1, according to Norton's theorem, after identifying the load resistor, short circuit it, right? So you can see a line here, short circuiting it, and we are finding out what is the current through this region, short circuited region. See, this is also very similar to our previous question. So whenever a resistor is in parallel with a short circuited branch, its effect is equivalent to 0, right? So the same thing applies here also. I have a 20 ohm resistor in series with a short circuited branch, that is IN, right? So the effect of this 20 ohm is negligible. So it becomes 0 since they are parallel to each other, right? Now this particular region goes off. So this particular region goes off. So now I will be restricted only with 50 volt source and a 5 ohm resistor. So this becomes a simple circuitry, right? A simple loop with voltage source and a resistor. So with the simple values, one can easily predict what is current I. Current I, right? The required Norton's current will be V is 50 divided by R. So 50 divided by 5, 10 amps. So that is the reason here we have chosen point number, that is option number 3. So for solving Norton's theorem, make it very clear, whenever this type of condition exists, that is resistor in parallel with a short circuited region, most value becomes 0, right? So with this small hint, we have to travel towards finding the other value. So once this short circuited current is known, as we discussed earlier, Rn and Rth are going to be same, right? So you have to kill the sources. So for killing voltage source, you have to replace it with a short, and for current source, it should be replaced with the open circuited, right? And when these two values are known, one can easily draw the Norton's equivalent circuit by having a current source in parallel with the Norton's resistance. So I hope this video gives a clear understanding about how to solve Thevenin's theorem and Norton's theorem. So we'll continue in the next lecture series. Thank you.